Recently, over at computerenhance.com, I posted a series on the 4 interview questions I was asked when I interviewed for a summer internship position at Microsoft back in 1994. Now, I already covered 3 of them, and it's time to cover the 4th and final one, but this one's going to be a little bit different because when I went and worked through the problem again in preparation to do it on the Lightboard, because I wanted to get a nice clean version where I had actually verified that I do all the math correctly. So, I wanted to test it in code and all that stuff to have one that I could actually present. I actually found something rather surprising. I found that the algorithm that was typically published and that most people know for solving this particular problem that I was asked in the interview question was actually not only not explained as well and more confusing the way that it's typically done in the publications, but it's also done less efficiently than it could be. And so actually now I'm much more excited about question number 4 because this is a bunch of new stuff. I haven't actually seen it done this way before, and so I'm kind of excited to work through this problem now because I've found some new stuff, and I would like to share it with you. So, question number 4 was outline a circle. Now, what the interviewer was looking for, unbeknownst to little Casey at the time, because I didn't know any of these things, the interviewer was not just looking for me to outline a circle by any means necessary. They were looking for me to outline a circle specifically with a very efficient, let's say Bresenham style, for those of you who know what it is, method of finding the pixels on the outline of the circle in a way that would be efficient for hardware of that time. Now, just to differentiate that, so people who aren't familiar with this sort of thing, or who are perhaps only familiar with programming things like OpenGL in a modern era, that sort of stuff, which is very different from how graphics was done in those days on PCs. If you think about how you might consider a circle these days, if we just talk about how we would find points along it, you're typically getting into trigonometry like right away. Like most people are going to be thinking about this sort of thing where they have a right triangle inside a circle. They have some parameter like theta and some radius r. That's the radius of the circle they're trying to draw. And they're going to think about stepping theta around the circle. So they will increase theta as it goes around to whatever their, full 360-degree representation, if that's 360 or maybe it's 2 pi or whatever, however you want, or tau. They're going to step theta through that. And they're going to use sine and cosine. So this is our cosine theta by trigonometry. This is our sine theta by trigonometry, the x and y coordinates of this point. So anyone who already knows how to do this, they might be thinking of it this way. Now, the problem with this conceptualization is that it's way too inefficient for hardware of that era. Hardware of that era was just trying to plot pixels and had very limited resources. Floating point was a big no-no. It was incredibly expensive to do floating point even at that point. Even in 1994, it was much more expensive to do floating point. And integer multiplies were still quite expensive compared to other things you might do. So you had to be very careful depending on which platform you were talking about. And this question was probably actually talking about something shifted slightly back, because if you were asking it in 1994, you were probably talking about 1990 knowledge or 1989 knowledge or whatever. So you're talking about an 8286, an 8386, that sort of thing at a maximum, and maybe even like an 8086 if you're really talking about, a little bit further back. So very, very limited support for the kind of things that we all take for granted today. It's sort of ludicrous to imagine a desktop PC not being able to do a lot of floating point operations, but that was the reality. So the idea that you were going to compute cosine and sine of an angle and then multiply it by a radius is just completely out of the question. The only way that anyone ever did anything like that back then was using kind of clever shift techniques and table lookups to compute the sines and cosines. So you're really not going to be able to draw a circle this way. And furthermore, even if you were going to draw a circle this way, you're still left with kind of a subproblem. Because when you are generating these points on the circle, you need some way to connect them. If you don't know, if all you're doing is plugging in a theta and getting out a point in the circle, you don't know how many pixels there are in between the last point and this point. So at a minimum, you would have to figure out some kind of algorithm to determine how far you had to step theta each time. So that's now a new problem you have to solve. Or you have to write a line drawing algorithm to fill in the spaces in between them. And then you're not really drawing a circle anymore. You're kind of drawing lines on a piecewise approximation of the circle, which is not really what the question is asking. So you can see how this is not going to work. Now, the reason that I don't think this is a good interview question, I mean, I don't really think that question-based interviews are the greatest idea to begin with. I've talked about that before. But the reason that this especially is not a good interview question is because, as you'll see as I'm about to work through, there are tons of really unique insights involved in working this through. And in fact, there's an insight that I had when I was working it through for this latest time that I haven't actually seen before. So it's actually a totally new one to add to all the other ones. And that is sort of the nature of problems like this. You don't just immediately see the solution. You have to think about it for a while. So it doesn't really make sense to ask people in the context of an interview, because you're asking them, if you're asking this kind of question, you're asking them to do the kind of work that is better done quietly and with contemplation, right? So right off the bat, we know we have to do something other than this conceptualization. And here is the first insight. And this insight is actually really crucial, even though outlining a circle today, you would not do it the way that I'm about to do it. This insight is particularly valuable even today for all sorts of reasons. And that is to recognize the difference between an explicit parameterization of something and an implicit parameterization of that thing. So this is an explicit parameterization of a circle. What I mean by that is if you look at how we've constructed this in like sort of light math notation, I'm as bad at math as anybody. So if you're scared of math, I'm right there with you. I will make this as intuitive as possible. We are talking about something, a function, where we're going to supply an angle, and then out of the function, we are expecting to get a point on the circle directly. So we are going to get our cosine theta, our sine theta. That is our explicit representation of the circle. We plug in any number here that we want, and we always get out a point directly on the circle. It explicitly goes from a parameter to the surface of the circle right in one step, right? That is how it works. But there's other ways of describing a circle, and you already know that. Probably the first encounter you have with a circle was not cosine and sine back in some kind of grade school or high school math class, right? What you probably saw was this. Right? X squared plus y squared equals r squared. That, we all agree, is also the equation of a circle. But how does that equation work? Because if you think about it, this equation actually doesn't give us any way to directly compute the surface of the circle, right? There's no parameter that we plug in. We can't just say, oh, 0.7, and out comes a point on the circle that's 0.7 around it, or 0.7 times 2 pi around it, or whatever else you want to parameterize this thing on. That's not what's going on here, right? So how does this equation tell us what a circle is? Well, it tells us using this. This is an implicit definition of a circle. It doesn't tell us how to directly find the surface of the circle. Rather, what it does is it tells us for a given point whether we are on the circle or not. In other words, if we were to rearrange this slightly and say f of xy, whatever we're going to plug in, equals x squared plus y squared minus r squared, meaning we move this over to the other side, right, equals 0, because that's what would happen here if we move this to the other side. Now we have a function where if we plug in any point in the whole universe, we can compute x squared plus y squared minus r squared, and r squared again is a fixed value. We just pick it for the radius of our circle. If it equals 0, then we know we're on the circle. So this is the implicit formula for a circle. It doesn't tell us where the surface is, but it tells us when we're on it. On the other hand, this is the explicit format. It tells us, oh, we can plug something in and get out something on the circle, but it doesn't tell us at all whether or not a particular point's on it. If we just had an xy, we would have no idea using this. It can't do detection, right? It can't tell us where we are relative to the circle at all. this can. So they kind of have two different, strengths. They both do different things. Now, this tells us more than just if we're on the circle, because this equals 0 here is the part that's doing that work. The fact that we look to see, is this equation equal to 0, is specifically picking out this radius. But what if we weren't on the surface of the circle? What would happen? Well, if we were further out, then the x squared plus y squared term would be greater than the radius squared, which means we would get a positive value here, right? And not only would we get a positive value, but the further out we go, the higher the positive value is. So we get higher and higher positive as we get further outside the circle. Furthermore, if we were inside, right, if we picked a point inside the circle, well, now x squared plus y squared is going to be less than the radius squared. And so when we subtract the radius squared, we're going to go negative. So inside the circle, we have negative. And what's more, the further inside we go, the more negative we get, because the smaller this gets, so this subtracts to a more negative number. Now, you may have heard the term signed distance field. This is a popular technique in rendering, in demo scene, in modern AAA rendering it's used as well. It's a very versatile thing that people use for doing rendering techniques. And you may have wondered, what's a signed distance field? Well, this is exactly what a signed distance field is. A signed distance field is something where you can put in some point, either in 2 or 3 or however many dimensions you wish, and get out a value that is positive in magnitude and increasing as you get further away from the surface on the outside. That's the signed part, positive on the outside, negative when you get further inside it. Signed, because which side you're on is the sign, and distance field because it's a field, it's defined everywhere, and its distance is, increases or decreases as you get further or closer to the surface. Now, I should point out here that when we say distance field, we do mean absolute value, because the signed in signed distance field means that as you get further away from the surface on the inside, well, if you wanted to know how far away the surface is, you'd have to do the actual absolute value, because you're not negative far away from the surface. You are as far away from the surface as the negative magnitude would imply. So really, if we wanted to know how far we were from the surface, we would actually do this, right? Absolute value of x squared plus y squared minus r squared. But you get the idea. So this is an incredibly valuable thing for certain kinds of rendering styles or certain kinds of, techniques we might use, where what we want to do is take a point that we already have, that we're wondering about, and we want to figure out what side of a particular boundary we're on, like a circle boundary. Well, that tells us, the sign tells us what side we're on, and also how far away we might be from that thing, and the magnitude tells us that. So signed distance fields are really fantastic. They're used in all sorts of things, and we can use this for our particular problem here. Now, it may seem like this doesn't help us, because if this was an equation for giving us points on the circle explicitly, how could it possibly be more efficient to turn it into a problem where we don't even know where the surface is exactly, and all we can have is sort of a guess, like a hot or cold, where we point somewhere and it says, hey, you're outside, and we point somewhere else and say, hey, you're inside, and about this far away, right? How could that possibly help us? Well, that's where the next insight comes in. And this insight comes from Bresenham. This is an actual person whose name was Bresenham, who figured out very early on in the history of computer graphics that one way that you could do things, instead of trying to figure out explicit equations for them, is you could use implicit equations and just turn things into a decision problem. Instead of asking yourself, how do I find all the points on the circle? You change the problem to asking, how do I start on the circle? And then how do I decide which pixel to move to next? Now, this may sound a little weird if you've never seen a Bresenham-style algorithm before, but let me explain it in detail, and I think you'll see it's actually really easy to understand and actually quite, it's quite brilliant. It's a really, really smart idea. And again, not something anyone will ever come up with on a light board in real time. So, if you imagine that we have our circle and we want to know how to start on the circle, Well, this is not very difficult. We know that the center of the circle is somewhere, and for simplicity's sake, so that the math will be easier for you to read, let's just say that it's at 0, 0, because we know we could translate our circle just by adding something to the values we compute later. So it should be pretty straightforward to do all the derivation without that. So assuming that we start around 0, 0, how, given just a radius, would we find points on this circle? Well, obviously, if we just use the points that are on the 90-degree marks, right? We know that on this axis here, the y is going to be 0. So our x-coordinate has to be r, right? It has to be the radius away to be on the circle. The same would be true over here. The x-coordinate has to be negative r. So we know that negative r0 and r0 are on. And similarly, if we cared, we could do the same thing in y, right? We could say, well, this is obviously y, 0, comma y, and this is obviously 0, comma negative y. So we know 4 different points on our circle, so it's free for us to start on the circle if we would like. How does that help us? I mean, it gives us the first part of the thing that I said we wanted, which is I was like, well, Bresenham algorithms are if you can start on something, then you just turn into a decision problem about which pixels to follow. So maybe you believe me that it helps for the description, but you don't really know what the rest of the algorithm is. So now let's take a look at what happens there. If we know we can start somewhere on the circle, and let's just start here. We'll start at r0. If we know that our x is starting out as r and our y is starting out as 0, we can imagine what happens on the pixel grid at that location and see something very interesting. If we imagine we have our pixel grid like so, and we are zooming in on this point right here, the point right there. This, let's say, is that point, and we're saying that this is exactly on the circle. So we're zooming in on just that, and there's that point, r, comma 0. If we're going to draw this circle going in this direction, up and around, right, counterclockwise, we know that we're already at the furthest extent, right? We can't go any further this way, because if we did, we'd be off the circle for sure. We're already at the furthest to the right we could ever be. So we know that all of these pixels are out. We're never going to move to those pixels. Furthermore, we're not going down. We're going counterclockwise, so we're going up and around. So we know we're not going to look at any of these pixels either, right? We also know that our tangent is starting fairly upward, right? It's going to be going in this direction. So we're also not going to move directly to the left. We would have to be kind of up here more past the 45-degree mark to be going leftward first. So we pretty much know that the only 2 pixels we have to look at are these 2 right here, A and B. We've effectively got it down to just 2, decisions, or 1 decision between 2 things, A and B. So all we need to know is, if we already are plotting this pixel, which of those 2, A or B, is the next pixel on the surface of the circle. Now, if we imagine this circle coming up through here, what we would intuitively also understand is that because pixels are at fixed, equi-spaced locations on the screen, the circle will not pass directly through either pixel center. Neither A nor B will probably, unless it's extreme happenstance, actually be exactly there. So what we really want to know is not which of these 2 pixels is the center, like on the circle, because it won't be. Neither of them will be. Neither of these 2 is right on it. But we do know that one of them will be closer. I mean, unless it's right in the middle, in which case we can use a rounding rule, but one of them will be closer to the circle than the other. So all we really need to do is figure out between A or B which one is closer. How would we do that? Well, we've already got the answer, right? X squared plus y squared equals r squared. We rearrange this into a function, x squared plus y squared minus r squared, that if we plug in an xy coordinate, what did I just say that it told us? The distance from the circle. So if we take the absolute value of what we get out of this function, we will be able to figure out which one is closer. So, do we know what these 2 things represent? Do we know how to find those points? We do. We know that we started at x equals r, y equals 0. So when we move up here, what are the new points going to be? Well, they're going to be x equals, r minus 1, to move backwards 1, and y equals y plus 1. That's the point A. And B would be the exact same point. This is A right here. B would be the exact same point as that, only the x would remain the same. So at any time, if we just want to consider neighboring pixels, you can see all we have to really do here is say y plus plus, right? We just increment y by 1 to get to the new location. And then we just have to determine, do we want to do x minus minus or not? Do we want to step 1 to the left or not? So it's free for us to come up with the two new candidate x and y coordinates because they're literally just an add and a subtract. That's it. And then we can just plug them into this equation. And we can say, if we say this is A and this is B, if we say if FA, absolute value, meaning the total distance, is less than FB, then we know which one to pick. If we plug in our A point to the circle equation, we will get out a distance. The magnitude, it's a sign distance, but the magnitude of that will tell us how close to the circle we are. The closer that is to 0, the closer it is to being on the circle. So the magnitude of FA versus the magnitude of FB tells us which one is closer. All we have to do is test. Whichever one is less, that's the one that's closer. Now, if we didn't care too much about efficiency, now the whole point of this exercise is efficiency, so we do, but if we temporarily pretend we don't, just so we can explain one more thing, we would almost be done, right? This tells us specifically how we would figure out which one to go to of these points. So we could draw our whole circle this way, we just have one simple problem. We worked this out for 2 points. Those would only be valid up until we got about to the 45 degree. When we get to 45 degrees, the circle changes from being mostly going upward to mostly going leftward. So then we would need to choose between two different points. The A and the B would actually be these 2 points right here, not these other 2 points. So this is kind of annoying because it means we'll have to basically break our circle into octants, it seems, and have one loop for each of these octants, which doesn't sound like very much fun, although we could do it, right? And we'd change which of these and how we work through our equations for each different pair of points. Not really the most fun thing to do. It would be nice if we could simplify that before working on the efficiency of this, just so we know we don't have to do it effectively 8 times. Well, here's where yet another insight comes in. If you take the circle, like so, one thing that is really nice about drawing circles as opposed to drawing other things is that circles are as symmetric as you would like them to be. We can pick any line at all through the center of this circle, and the circle's 2 halves created by that line are symmetric. If we look here, for example, the y-axis, this half and this half are perfectly symmetric. That means you could mirror one side and get the other side. So if we think about what this implies, we know that using our little AB technique, like I said, is good up to about the 45 degree mark. We could draw this octant of the circle quite easily using just what we already talked about. When we get to here, however, we had to switch the points. So the question is, with just this, if all we had was just that one algorithm, exploiting the symmetry of the circle, could we draw more of it than just that octant? Well, like I just said, it's free to mirror this thing. So when we are picking points here, we're going to have a bunch of xy coordinates. Those xy coordinates will be all the pixels along this octant. Well, if we also wanted to draw this octant right here, all we would have to do is mirror around x, right? I should say mirror around the y-axis, which is mirror the x coordinate. So if I was to negate my x coordinate, flip it around, all of these points now become all of these points. That means that for the same price as computing the xy over here, I can also have all the xy's over here just by negating. And hey, if I can negate across the y-axis by flipping x, I should be able to negate along the x-axis by flipping y as well, right? So if I was to plot negative y, now I flip here. And hey, I might as well flip this one too and get this octant out of it, right? So now, by flipping all of these in all of the different permutations, I've drawn 4 of the 8 octants. But we don't have to stop there. It's also really cheap for us to flip around the 45s, right? Flipping around 45, what does that do? Well, it just swaps, or x and y. If you think about these x and y coordinates, right, this starts with x equals the radius and y equals 0 and works up to x and y being equal to each other at the 45. If we were to imagine going the opposite direction, this is where y equals 0 to start with, right? I'm sorry, y equals the radius to start with, and x equals 0. And then as we go down, we get x equal to y. So if we just swap the two parameters, we can take this octant and mirror it into this octant. All we have to do is instead of xy, we plot yx. And I think you can see where this is going. Once I have this, I can flip that around this axis, around this axis, around this axis again, right? So by doing all of the permutations this way as well, I now have all 8 octants accounted for. So this means we can concentrate all of our mathematical simplification and our work on the algorithm on just this for just these 2 points. That's all we have to do. We don't have to worry about what will happen at each of these changeover points when the derivative goes, between mostly upward to mostly sideways to mostly down, that sort of thing. We don't have to think about any of those sorts of things. We could just do one octant where we know it's always going up and slightly left, and we can mirror it to everywhere else. Now, like I said, this problem is just incredibly long and involves so many insights. You've already seen several of them. There are several more to come. But I've run out of space on the Lightboard, and this is already going to be a very long video, so rather than you watching me erase the whole thing, what I'm going to do instead is snap my fingers and do a jump cut here, where we will jump cut to me having already erased the board, where we will then start to work on the FA less than FB part of this, which we now know is the crucial part of our algorithm. So here we go. So we now know that all we have to do is take our function, which is x squared plus y squared minus r squared, which we now know gives us our signed distance to the circle. And we just have to say, all right, for the 2 candidate points A and B, which one is going to have the lesser magnitude? Now, we know that both A and B are going to have the same y value, right? Because each time we're always looking 1 up. The only question is, do we move to the left or not? So every time through our loop, if we imagine actually implementing this when we go to type in the code, we're always going to increment y. So the only real difference, the only 2 things we're talking about here, are whether or not we do x minus 1 with our new y coordinate, or do we do just x with our new y coordinate. This is all we have to determine. For some given y, which we now know we've stepped to, do we want to go to the left, or do we want to stay in the column that we're in? And again, to do this, really straightforward, all we have to do is say, is the magnitude, right, of the A function, is that going to be less than the magnitude of the B function? That's all we need to know. So the first thing we need to do is expand this out. We basically need to take this and expand this into its actual functional form. So here we have x squared plus y squared minus r squared. We need to substitute this in. So on the A side, right, if we're going to do magnitude of A less than magnitude of B, if we need to start substituting this in, well, this is A here, so we get the magnitude of x squared, which is now x minus 1, plus y squared, which is still just y, minus r squared. There's our left side. And for our right side, we have magnitude of B, which is just xy, so it's literally this exact expression. just with the magnitude taken. So these are exactly what we need to compute. And like I said, we could just compute them. We could literally just do this, compute these, take their absolute value, and then see which one is less. The only reason we're not going to do that is because we're worried about efficiency. And if we look at what has to happen here, well, there are several adds and subtracts, and so, that's okay. Maybe we'd like to reduce the number if we could or whatever, but it's not really that many. The problem is all of these squareds. The squareds are a huge problem because if we're expecting integer multiplication to be slow, especially compared to something like an add, we have a really nasty situation where we're going to have to do a ton of it. The r squareds we could compute ahead of time because the radius isn't changing, but the x's and y's are. So if the x's and y's are changing, we're going to constantly have to do at least 2 multiplies for this side to do these 2 squares, and 2 multiplies for this side to do these 2 squares. That's just plain too expensive. So how would we get rid of some of these squareds? Well, ideally, we'd like to start working with these equations more and perhaps figuring out ways to simplify this entire comparison. But we do have a problem here. These are inside absolute values. And if you've ever tried to work through math, you know that absolute values are a huge pain. There are ways we can try to work around it, like a lot of times people will do things like square both sides or things like that to try to remove the absolute value. But in this case, we actually have an advantage. We can do something that we wouldn't normally be able to do by applying yet another insight. Now, this one is perhaps a slightly more tenuous insight, and the reason I say that is because the first time I've ever seen it is when I came up with it when I was working through this problem yesterday. But I'm fairly certain, because it's fairly simple, that it is correct. And here it goes. All we are using this for, the only thing we need this expression to do, is to determine which of 2 sides is of greater magnitude. That's the only thing that we're going to do with it. We're never going to actually use the value. So really, the only thing we need to preserve is that if this side was greater in absolute value, then it needs to remain that way afterwards to whatever operation we're going to do. Like, we just can't violate that. And the same is true of this side. We have to make sure that if previously it was greater, it has to remain that way. They have to remain with their relative comparison. Well, think about what happens in the 3 cases we actually have. We know that there are only 3. The first one is the one that we expect to have most often, which is when the circle passes between the 2 points. And this is the case we really care about the absolute value part of things, because we need to know which of these pixels is going to be closer. As this moves, either side of the center line, we're going to get a different answer. Now, the other cases are when it passes completely on one side of both pixels and completely on the other side. It could get, as close as you want to this particular center, but it's going to be on this side of it, or as close as you want to this center, but on that side of it. In these cases, we know exactly what we want to pick for these 2. It's always going to be point A in this case, and it's always going to be point B in this case, because since we know inside that first octant, moving to the left always reduces our value. It gets us closer to the center of the circle. There's no way that we can ever be, this close to the circle here, move left and end up getting closer to the circle surface somehow. And the same thing is true here. If we know that the circle passes to the left of A as opposed to the right of B, we know that A is always the choice because there's no way to move to the right and get closer to the circle. That's just not possible. So we know in each of these cases exactly what we want to pick. In this case, we don't know. We actually need the comparison to tell us, and we need the magnitudes to be correct for that because we need to pick them. Well, what are the actual values here? What are the actual signs of these things? Well, if the surface passes through, in between the 2 pixels, then we know that this side is going to be negative and this side is going to be positive, because that's the definition of what it means to pass on either side of this surface, right? That's just what the function tells us. In this case, they're both going to be positive because they're both outside the circle, and in this case, they're both going to be negative because they're both inside the circle. We know exactly what we would do in the case we care about to take the absolute value, trivially. If we want A less than B, if we want to actually do this comparison, then what we want to do is negate A. We don't need to do anything to B, it's already positive. So the absolute value of B in this specific case is just B, and the absolute value of A in this specific case is negative A. So this is all we would have to do is negate one of these two values. That would give us our absolute value basically for free, for very small cost here. We can do that trivially. So the question becomes, could we just do this, period? Can we just do that and avoid ever thinking about the absolute value ever again? Well, recall what's going to happen here. If this is true, we pick A. If this is false, we pick B. So we would want our new, when we create this sort of faux absolute value that we did here for this case, all we really need to do to just use that permanently, because this is the case we care about, is prove that it doesn't break either of these two cases. So we want negative A less than B. In this case, we want to pick A, so we want this to be true in this case. And we want it to be false in this case, so we'll pick B. Well, let's see what happens. We know that we've got two positive numbers in this case. If we do negative A less than B, it's going to change A to a negative and leave B as a positive. That's what this will do. Will a negative always compare less than a positive? Yes, it will, right? So we will always get true in this case for this modification. This fake absolute value will always return true in this case. It won't have the correct magnitude anymore. The value that we get back as negative A is totally wrong, right? It's not the magnitude of this distance anymore because it's negative and it actually should be positive. But we don't care because we're only using it to make a decision, and the decision will be correct. If we then look at case B, what happens there? Negative A, B, well, that will flip this sign. So now we're going to have a plus on the A side and a minus on the B side. We want this to be false. That is how we will pick B. Well, if we are going to compare less than of the plus and the minus, hey, guess what? We can never have a plus be less than a minus. So once again, we always pick false. So it turns out that in this case, we don't even have to work through the math because there probably are substitutions we could do here, using the fact that we know, like I said, because of the ordering of these points, and we know that in this octant going to the left always makes you go less than. We do know some things, like we know A is always less than B. This is just always true, right? A can never be greater than B, just as a value. Not the absolute value, but the actual value. We know that. So you could probably work through the math and prove this in an algebraic way too. But visually, in the geometric case, we can clearly see it's true, and I usually like those better. I have an easier time thinking through them than trying to hunt through which substitutions I can do in algebra to make something come out. I'm not as good at that. So this gives me very high confidence that we can actually just do this, and it will produce the exact same result as the actual absolute value in all of these cases. Like I said, this is kind of a new thing, though, so it warrants further scrutiny, certainly. But I'm pretty sure, based on this analysis, that it's correct. Now, this is the second time I've tried to explain this. The first time, it didn't make any sense. This is something I just worked out yesterday, so it's not like I actually have as solid of a grasp on it as maybe I should. I think this one went better. It explained my reasoning better and how I worked through it on my actual notes. But what that means is I already have the rest of this presentation done, so I don't even have to snap my fingers this time. I can just use like the power of my mind to jump us over there, and I will try to do that. This I can change to being this actual thing by just kind of focusing on it if this video edit works properly. Let's see. We can now finish what we were doing here, right? We can continue to work through these and simplify these equations. So let's see what we actually end up with. Well, first off, we need to expand this term on the inside. So this is the x minus 1 squared. That's going to be x squared minus 2x plus 1, using, again, your math homework from grade school, plus y squared minus r squared, in parentheses. We then know that we want to test that versus x squared plus y squared minus r squared. We have a negative in the front, so we want to go ahead and distribute that. Negative x squared plus 2x minus 1 minus y squared plus r squared less than x squared plus y squared minus r squared. We now need to transfer everything from this side over to this side. Because if we think about how we're going to use this, what we would like to do is boil this down to the simplest possible form. So combining terms is going to be helpful for us to reduce operations. But also, if we can make this whole thing just be a comparison against 0, that again improves the chances that an assembly language implementation, which is what you would have cared about back in those days, right, is going to be very efficient. Because testing against 0 is basically free, whereas testing against something else involves doing a subtract, right? So we're going to transfer all these things over. The x squareds double up because there's an x squared here. It comes over and it's minus. The 2x minus 1 remains the same. The y squareds also double up, and the r squareds double up, which leaves us with this. And we can quickly identify here that there are some constants. Minus 1 is a constant, and plus 2r squared is a constant. So gathering our constant terms together, since we would assume those will be ripe for precomputation, we have this. Negative 2x squared plus 2x minus 2y squared plus c less than or equal to 0, where c is equal to 2r squared minus 1. So this is actually all we really need to think about to do our classification. Negative 2x squared plus 2x minus 2y squared plus c, where c is this thing we can pre-compute if we so choose. Now that's not bad, right? We're down to just 2 multiplies, and then, for doubling you can add or shift. Usually adds faster on like an 8086 probably, although if you're only shifting by 1, it's a wash. You can probably do either. So down to 2 multiplies, and getting it down to 2 multiplies is much better. So we're definitely making progress here, but 2 multiplies is probably still 2 multiplies too many. So ideally, what we would like to do is get rid of them entirely. And is there any way that we could actually get rid of these entirely, right? Well, if we're just talking about showing up, right, if we're just going to pop on the scene and pretend that we have random x and y coordinates, no, there isn't any way. We would just have to do this equation. We have to do the multiplies that we have to do. However, we do have we've already benefited, you might say, from the insight that that is not what we're doing. What we're doing is taking single steps along pixels. We're just moving from one pixel to the next pixel each time. And exactly as we did originally, where we said, hey, we can simplify all the stuff we're doing by, instead of considering all, like, how do we generate points on a circle, what if we only had to generate points that are next to an existing point in a circle, and suddenly everything boiled down to this really simple choice between two things? Well, we can use that same idea, that same sort of concept of turning it to a step, just going step by step, since we know that's what we're going to actually write in code, to help us get rid of these multiplies. And how would we do that? Well, this is actually something that is very well understood, but not that widely known, I guess. It matters a lot to a very specific group of programmers who do this sort of thing all the time, and everyone else has never heard of it, and basically what it boils down to. We can trivially take something complex like this and turn it into something much more straightforward by using something called the digital differential analyzer. Digital differential analyzer is the sort of blanket term for what I believe came out of the Bresenham style algorithms, because it turns out that idea of turning things into steps, there's actually a lot of things you can do with that. You don't have to just think about error, like how far am I away from the function I'm actually trying to do. You don't have to just think of it as doing that. You can actually just think of it as, if we're doing stepwise deltas, well, couldn't we just phrase all of the things we're doing in terms of how they change from one pixel to the next pixel, or from one step to the next if what you are simulating isn't pixels, right? So digital differential analyzer can really help us here. And in order to show you how, what we need to do is take this equation, negative 2x squared plus 2x minus 2y squared plus c less than potentially 0, is it? We're asking the question, where c is 2r squared minus 1. We need to take this and apply a digital differential analyzer approach to it. Now, again, in order to do that, I will quickly run out of lightboard room. So I'm going to snap my fingers again. And then we're going to look at what will happen if we apply a digital differential analyzer style technique to this equation in order to compute it more straightforward. So how would we apply the digital differential analyzer technique to this? Well, recall what we're actually going to be doing here. We're using this expression. We're going to compute this effectively on every step through our loop. And we're going to see whether or not this is less than 0. That's how we're going to decide whether we take the left pixel or the same column that we're on. So what that means is we know this value is something we could carry along with us. We could, for example, compute it once before we start our loop using whatever we want, any method of computation, because it's outside the loop, so it could be slower. We can compute some starting value, and then every time we step, either up or up and to the left, we could make sure that we calculate the delta that we would need to apply to get it there and apply that. In other words, if we say that this is some new function that we want, this right here, could we rephrase our computation of this in terms of the change that happens when we go from the pixel we're on to the upper pixel or the upper left pixel? And we would have to do both of them, right? We would have a different amount that it would change. So really, we're just taking a delta. We're saying instead of computing it whole cloth, we're going to compute the change and just remember what that change is. Well, how would we do that? Pretty straightforward, right? If we're at a particular pixel, dxy, and we want to know what would happen if we move to a pixel like dxy plus 1, for example, all we have to do is plug that into our equation. So x stays the same, negative 2x squared plus 2x minus 2. Y squared is now y plus 1. Y plus 1 squared plus c. Expanding this out, we get negative 2x squared plus 2x minus 2y squared. This is going to be plus 2y, which becomes minus 4y, right? Minus 2 plus c. Sorry to do that all in one step. I shouldn't. I make careless math errors all the time. So this is what would happen when we move up y in 1, right? This is what its value would be on the current pixel. This is what its value would be if we moved up 1 pixel. Well, if all we need to do is update from a known value, which we already are saying we would keep in our loop, to the next value when we move up, what would we do? Well, we just write that subtraction. We take this, we subtract where we started, which is this, and we would get the difference of these two equations, right? Now, if you look, they're highly similar. The 2x squareds are the same, the 2x's are the same, the 2y squareds are the same. So they're really the only difference, and even the plus c would be the same. So the only thing that happens when we subtract the two, we're just left with just this. It's just negative 4y minus 2. That's all we've got, right? So this is some really good news for us, isn't it? Because this means that every time we increment y, we don't have to recompute this whole equation. We can just remember what its value was and just do minus 4y minus 2. That's a very simple shift of y and a subtraction of 2. That's all we would need to do. Now, if we wanted to, and we were thinking like, well, maybe the shift, it's going to have to be a shift up by 2, right? If we want to do 4 times y, right? I don't know how we want to write that. 4 times y in computer notation. That is going to be equal to y shifted up by 2, right? And unfortunately, on really old computers, like an 8086, shifts cost a cycle per bit typically. So if you shifted up 1, that was a certain expense, but if you shifted up 2, it's more expensive. So if we wanted to, we could even continue, and I'm going to do it just to show you what happens when you fully follow a digital differential analyzer all the way to the bottom. There's no reason we can't rebrand this equation yet again, right? Now, I just want to be really clear because if you've never seen this before, this might be kind of confusing. What we're saying is we have a loop, some while loop or whatever, right? In fact, literally in this case, we're going to be doing while x is greater than y, right? We're just going to go to that 45-degree point. Outside the loop, we're going to compute this value for the starting x and y. And of course, y is 0, so that goes away. So it would just be the x would be equal to r. We'd compute negative 2r squared plus 2r plus, 2r squared minus 1, right? And hey, the r squareds cancel. That's a little foreshadowing for later. But anyway, we compute that in startup, and we just have that value. Now, every time we step up 1 pixel, which we know we're going to do every time through the loop, all we have to do is take this value that we've stored and add negative 4y negative 2 to it. We just add that every time. That's it. Now we don't have to compute this anymore. No more multiplies. However, we still do have to do this shift, and maybe that shift is expensive. Let's say we were on hardware where that shift is expensive, or some embedded thing. We're making an FPGA. Who knows why? Even today, this might matter in some esoteric circumstances. Well, we can make this yet another delta. We can ask what the delta of our delta is. And if we want to do that, then we just have to make up a new name for this, right? We can just say, all right, we've got yet another equation, which is e, I should say yet another function, which is going to be 4y minus 2. And we do the exact same technique. What happens to the delta when we move up by 1 pixel? Well, same thing applies, negative 4y plus 1 minus 2, right? Now you'll notice x is no longer involved, so really we don't even have to think about x if we don't want to, but it's, however you want to do the notation. If we then do the exact same procedure, y plus 1 minus e xy, if we do the exact same procedure here, all we will see is that everything cancels exactly as it did before. So negative 4y, negative 4 minus 2. Right? That's what happens if we do this y plus 1. We end up with, excuse me, we end up with this. So if we do our subtraction now, the 4y's cancel, the negative 2's cancel, and we're just left with negative 4. That's all we've got. So now we've gotten down to a constant, just by taking the delta twice. So if we want to do this in a loop, again, incredibly simple now. We have 2 values we store. First, we store the value of negative 4y negative 2 and the value of negative 2x squared plus 2x minus 2y squared plus c. 2 basically accumulators or values we carry in our loop. We compute them on the outside of the loop. Each time through the loop, we add our delta value here to our double delta value to our delta value, and we add our delta value to our main value. And since we actually did this as a difference after the fact, we would really do it in the opposite order. So we would add our delta value, this accumulator that we're storing, we would add this to our main value, and then we would add this to the delta value. And we could have solved it the other way around. We could have done it as a y minus 1 to y, and then we would add them in the opposite order. But you can see what I mean there. It depends on how you wrote these equations initially. So if we just assume that all of this stuff is now taken care of. We don't have to do any of these multiplies that we don't want to. We know exactly how to move as we go up in 1 pixel. The only question that we have left is, what do we do when we actually have to move to the left by 1 pixel? Because this whole procedure only accounts for moving upward. It never accounts for moving left. And since we need this value to be correct wherever we move, and it is definitely dependent on x, even though moving up doesn't require us to do anything with x, moving to the left would. It would require us to update the value of this based on the delta in x. Now, it may come as no surprise that the exact same procedure can be used to do this for x. Because if we could do this for y, there's no reason we can't do it for x minus 1. So if we say, all right, what is dx minus 1 y? That will tell us what to do if, when we look at our d value, we find that we actually do want to move to the left because it's less than 0. We now need to update our d value for the next step to account for that x motion. So we need to know from the current y, if we were to step 1 to the left, what would happen? Well, same exact equation. It's literally the exact same thing, only we're going to plug in x to it now as x minus 1. So negative 2x minus 1 squared plus 2x minus 1 minus 2y squared plus c. That's our equation for when we move left by 1. Now, of course, we have to do all this again. This is going to be x squared minus 2x plus 1 plus 2x minus 2 minus 2y squared plus c. Sure hoping I didn't mess something up there. Minus 2x squared plus 4x minus 2 plus 2x minus 2 minus 2y squared plus c. I think I've got everything right in there, but you'll have to forgive me if I've made some errors here. It's hard to do this on a light board. So we're going to do the exact same thing. We're going to subtract the original equation from this one, because what we really want to know is what's the delta between this, where we're going, and where we came from, right? That's how we're going to do our step. So the negative 2x squareds cancel because they're the same in both. The plus 2x's cancel because they're the same in both. The 2y squareds cancel because they're the same in both. And the plus c cancels because they're the same in both. And we are just left with, lo and behold, 4x minus 4. Look familiar? The only real difference between these two is that there wasn't a leading negative, because the x was minus 1 and the y was plus 1, so we ended up with a slightly different step. But that's the only difference. We're going in, and it makes sense, right? Because x and y in a circle are symmetric, right? It's a symmetric equation. They're both x squared, y squared, both the same. So it makes sense that we got the exact same thing, only we have a sign difference, and the sign difference, of course, comes from the fact that when we are considering what step we're taking, in one case, we're going along the negative direction for that axis, and the other case, we're going the positive. So it makes sense, right? It's intuitive that this would not be exactly the same, that there would be a slight difference between the two. But otherwise, as you can see, very, very similar, right? Everything is, it's almost exactly the same. There's very little difference between the two. So we can do the exact same thing we did before. If we imagine that this was actually going to be, a different one in this particular case, now we have so many of these, we're down to capital F now. Can you imagine having to do this on a whiteboard for an interview question? Oh my God. So anyway, if we actually imagine that this is now our new equation that we actually want to do a delta for, when we do the exact same process here, we want to know what happens when we move to the left, like so. How are we going to update this? Well, we're going to update this by plugging in x minus 1 to the equation. That gets us 4x minus 4 minus 4 again, which of course is 4x minus 8. Once we're at 4x minus 8, we have to do the subtract, right? We have to do f of, and I'm going to need even more room here, f of x minus 1 minus y minus f of xy. We now need to subtract this from this. The 4x's cancel, and all we get is a plus 4 over this, so it's back to negative 4. Now, this is a somewhat surprising result. We have a -4 as our update and a -4 as our update. Both axes, again, exactly the same as they move through. The only difference is how we initially seed them. One is a -4x and the other is a +4x. But that's it. So now we have literally baked the entire thing all the way down, from starting with having to do cosine and sine theta times r to get our points using theta to move around and having no idea how to step, all the way down to all we need to do is subtract 4 from two different variables, depending on whether we're inside an if statement, right? So we subtract 4 from one of our variables. We also update our carried, decision value there, d. We then check what the value of d actually is. And if the actual value of d is less than 0, we would update the other two, that carried d value using this step, and update the step value by -4. That's it. So it's incredibly simple now. It's just adds. There's nothing else, right? A few handful of adds and a check against less than 0. Now we can also simplify the startup. Because, like I said before, we know that we sort of have these initial values we have to compute. We have to compute 4x minus 4 as our starting value for our x motion delta, right? Or the thing that we're going to add to the delta value. I don't even know what a good num. Maybe the digital differential analyzer guys would know. I don't know how you keep your terminology straight in these. It gets very confusing. As we'll see when we look at the code, it's actually very simple to understand in code. It's just kind of hard to keep the math notation from having just way too much stuff. But either way, we have to do our 4x minus 4. We need to do our -4y -2. And we need to do our -2x squared plus 2x minus 2y squared plus c. We need to do all of those at startup. What if we care about our startup time for like small circles? Well, all of this stuff is incredibly simple as well. Y at startup is 0. So the starting value for -4y minus 2 is just -2. It just loads the constant. Trivial, right? And similarly for 4x minus 4, which is now down here off the board, well, 4x minus 4, x is just the radius. So 4 times the radius is just a shift up, which would be very simple to do at startup. It's only a few cycles at startup. So again, trivial to initialize those two, very, very simple. How about this? Is this difficult to initialize? Well, if x equals r at startup, which we know, and y equals 0, this term is gone. -2x squared is -2r squared. R squared is here in C, so -2r squared and 2r squared actually cancel. And we're just left with 2x minus 1. That's our entire startup. 2x minus 1 is just 2r minus 1. And hey, guess what? 2r is just r plus r. It's one add. We already need it to initialize this. So we do r plus r, and it's that minus 1 for this value. R plus r, since we've already computed it, gives us 4r, which is our other initialization value. So we actually turn that into just an add as well. We don't even need the shift anymore. It's now embarrassingly simple to look at what it takes to draw a circle. Let's go over to the computer and see exactly what I mean in code. As luck would have it, all of our math boiled down to something very simple, so our code is actually quite simple. Once we define the center and radius of the circle, and I've just made a little fake bitmap here that we can draw into, and then print out to the console, just so this is easy to run anywhere with no graphics libraries or anything like that. The loop that draws the circle is incredibly simple. First, we do that add of r to itself to create, 2r basically. And that's, like I said, just because that's the easiest way to compute these startup parameters. We start x at the radius, like we said. We start y at 0. We initialize our dy value to -2 and our dx value to 4r, using that computation again, -4, and our initial decision value to 2r minus 1. Again, all of that is just exactly the math that we just said when we looked at what the startup value should be on the board. We then enter our loop, We loop while y is less than or equal to x. Again, this will tell us when we've reached the 45 point. And of course, at the 45 degree point, we want to actually draw that pixel so it's less than or equal to, not less than, so that we don't have a dropout pixel there. We then plot the negative and positive versions and the swapped versions of the x and y coordinate that we're on. You can see here we take the center x, center y, and we just do all the possible permutations. This draws all our octants, setting all of the pixels in our bitmap to 1 in those locations. Since we know we always move up by 1 row each time, we always do a plus plus y here. And of course, we're going to update our decision value using our step value for y and updating our step value for y by its step, which is -4. Then all we have to do is determine whether we want to go to the left. Again, the d value tells us that by saying if d is less than 0, then we can go ahead and do our x step, which happens exactly the same as the y step, just with the dx value instead. And of course, x goes to the left, so it's subtracted rather than added. That's actually it. But because this is so simple, you might also consider the branchless version of this. Since we know that the sign bit of d is what will determine whether we're going to the left or not, if we simply do an arithmetic shift of 31 down, which also on an Intel processor you could do the CWD instruction as well to replicate the sign bit, you then have a register of all ones if we're supposed to go to the left, and all zeros if we're not. So if we just AND our existing step values that we would do if we were taking a step to the left, by that mask, they will either be what they should be for a step to the left or 0. So we can do our step every time if we want to by just masking the values first, turning this into a completely branchless algorithm. And of course, we can also do that with the x. We don't have to actually do an AND with the mask because the mask is already 0 or -1, and so all we have to do is directly add it. That's really it for the code. All we have to do then is print out the actual bitmap to the console so that you can see it. And of course, I print it as 2 characters each time for every pixel because characters are much taller than they are wide. So our circle would come out as like an oval if we printed out a character per pixel. This makes it more square and makes it look more like it actually should look if the pixels were square, which is an underlying assumption of all graphics. If we go ahead and run this code, you can see we get the circle we expect. It's exactly correct. And I did actually verify that it produces the exact same pixels as like a standard Bresenham, which is actually a more expensive algorithm. So I do think that this particular algorithm is actually the most efficient one in terms of the simple operations that it does as compared to anything else I've actually seen. Which is great, because as you saw, the derivation is very straightforward and easy to follow. The really only hard part about it is the fact that you have to chug through so much term simplification, but the actual ideas behind it are very straightforward. And it just so happens to result in the most efficient code that I've seen yet as a nice bonus. That was an incredibly fun problem to work through. I really love it when you look like you're going to drown in math and it's going to be like, oh, this is never going to be anything. That works particularly well. But then everything just lines up perfectly, and it turns out that the actual code you need is so simple. And yet when you look at the code, it's now like if you hadn't gone through that whole process, you'd have no idea. It's like, how could this possibly be drawing a circle? But then when you realize what each piece is doing because you've worked through the whole thing, you're like, oh, okay, I see. That's basically like creating this stepwise version of a squared function. And it's like, oh, wow, okay, that's really cool. If this is the sort of thing you like, honestly, we don't tend to do nearly this much math on computerenhanced.com, but we do this sort of thing, meaning we always try to follow things all the way into the details and figure out what's really going on. And a lot of the time we find out that things we wanted to do that may have seemed complicated at first are actually really simple when you understand what's going on under the hood. So if this is the kind of thing that interests you, please check out computerenhanced.com. Right now, we're doing a performance-aware programming series where we do this kind of in-depth analysis on software performance, which, again, is not really math, but it does involve doing things like learning some assembly language and how to investigate how things are performing and figuring out how CPUs do things. It's a lot of fun, and it helps in everyday programming because it allows you to make better decisions even when you're working in high-level languages because you know what's actually going on under the hood. So that's it for my series of work-throughs on the old internship problems from years ago. After this, I will be doing a brief recap and talking about a couple other things. And then we'll be back to the Performance Aware Programming series. So if you're already taking it on computerhance.com, I will see you back there for that very soon. Until then, have fun programming, everyone, and I'll see you on the internet.